So even if we use more modern user interfaces, you would agree with me that these replies look a little bit futuristic even now, right? Somehow magic. But I'm not here to tell you about that, because I think you'll be more interested to hear what's working behind the scenes. If we look under the hood, we see a series of HTTP requests, authenticated HTTP requests that will go to some service, and a service is running in a container, and a container is running probably in some virtual machines, and this virtual machine is running likely on a server somewhere, and so on. But before we get to the infrastructure part, I want to show you a little bit what's going on behind the scenes in the AI model. The AI service will use some form of AI framework that eventually will use a large language model, LLM, pre-trained. And the large language model will guess the next word. That's all it does, right? We give it a prompt, and it will return the most probable word. And then it will append the new word to the previous prompt. And we obtain a new prompt. And here we go. We have another next best word. We append it again. We have a new prompt. Again and again, and so on, and so on, and so on. So the effect is that of a thinking machine. But really, what's going on is that this model has been trained on a large collection of books, newspapers, internet media, code, exploits, vulnerabilities, specifications, PDF, and so on. And the next most probable token, the next most probable word, is based on what the model has seen during training. There's a bit noise back there, a lot of noise. We can extend the same reasoning to anything. Image generation, video generation, and so on. Code generation. Anything really that we can represent with a numerical representation. So everything we can think of. With coding framework and more complex tasks, the idea is slightly more complicated. Behind the scene, there is more orchestration going on. Some is deterministic orchestration, the effect of a choice pre-programmed. Somehow is probabilistic decision based on the output of some LLMs that will need to be called with the right prompt at the right time. Maybe we can call an outside service with an API, or as they used to call them today, MCPs, right? But the essence of the problem is the same. We have an LLM that calculates the next word. So let's see how an LLM works inside. An LLM is a multi-step transformer. It'll start from words or tokens, and it will transform them into numbers, and then it will perform a series of transformations between numbers, and finally back to words again. First, the LLM has to learn how to represent words. And it'll start with a vector representation, which we call embedding, that basically maps a word to a unique vector in a space. And the interesting property in case of natural languages is that we want the LLM to learn to cluster together words that have the same meaning, the same semantic. And the opposite is also true. Words that have opposite meaning will be encoded in a different way. And the spatial relations between this opposite word can be measured, right? So now we have this representation in mind, and what training really means is that at each stage, the LLM will learn how to best set these weights, these parameters, in a way that words with similar meanings or tokens or whatever information we need to encode that needs to be clustered together will stay clustered together, and other properties in common, depending on what we want to encode. So these operations are repeated over and over through multiple steps, and at each stage, we encode a property that is of interest. It can be the semantic of the words or the tokens. It can be the relation between tokens. So how far apart two tokens are in a text, which one comes after the other, and so on. And these operations are just repeated over and over, continuously updating the numbers, the parameters, the weights, until we're happy with the prediction error. And when we're happy, we call the model train. The interesting thing is that the last layer, we can query it. So we can ask it, hey, what's the best conference in this time of the year? And the last layer will return as a probability distribution across all possible words that are seen during training, and we pick the obvious one, no hat. So really, a model is a collection of weights. And training calculates these weights. We're currently talking about trillions of parameters, probably, because we don't really know exactly how many parameters are in these models, let alone the architecture of the models, because these are, quite expensive objects to train. And this is not something that you can train on a general purpose hardware. Even if you use hyperthreading, or this doesn't scale. We can give you 198 CPUs in one instance, and you can rent as many as we have. But this doesn't scale, because we have, of course, network latency and so on. So one approach is to use general purpose GPUs to scale the problem, to make it parallel locally. Another option is to use an ASIC. An ASIC is an application-specific integrated circuit that you can design in a way to optimize that specific calculation. And it's designed to run parallel operations at the scale that you need, as much as you can fit in the silicon. Here is our latest silicon. It's called Trainium 2. We launched it last year. And if you look inside the silicon, there are 3 core components. Component number 1 is called systolic arrays. Systolic arrays are processing elements. Those are the elements that do the math, the actual calculation. And these will receive numbers directly from data buses that connect them to high bandwidth memory. There are no instructions here. There's no interpretation of a program. The systolic arrays will just continuously receive numbers. As soon as the numbers are presented to their gates, they will just calculate. There's no instructions here. There's no program to load. And all these components are connected together electrically by a so-called interposer that creates the electrical connection between these components. Great. So now we have our fast compute element. How do we make it useful? How do we make it interfaced with the software world? Well, we need to package it first, then we need to put it on a printed circuit board, and we need to give it an interface to the software. And to do that, we need a few more components. The most relevant one is so-called management microcontroller or management SoC. This is a fairly powerful, normally a fairly powerful system on chip that can run anything from simple firmware to full-fledged operating system with multiple cores, very powerful. And the 4 most important functions of a management SoC of an accelerator are, number 1, needs to control the reset line of the card so that we can reset the silicon when we need. We can bring up the silicon. We can set up the PCIe interface. And most importantly, we configure the security settings of the accelerator, of the actual ASIC. Because we want a security model where the user space, or better, the host, can use the full PCIe link space without having to worry about creating issues in the silicon that may affect other customers. Our threat model wants to assume that you can rent an instance and run as root. You can write your own driver and use the PCIe link as root. But then we need to draw the line at the machine level, which means that the management SoC has to enforce the security model of the card. The OS is completely in your hands. We don't want any OS-based isolation here. In this way, every customer can rent an instance, use the accelerator, and when you're done with the LLM training, you can just destroy the instance, and the instance will also, and the management SOC will also take care of scrubbing the data. You will not find the data of a previous customer in the DRAM of the accelerator, of course. So the management firmware running on that SOC is certainly key. And if we find a vulnerability in there, it's something that we want to patch. But at the end of the day, we can just patch it. I mean, it's a software issue, right? And regardless of how deep that software issue may be, it's ultimately just a software issue. How about vulnerabilities in hardware? Well, hardware is designed by writing code, ultimately. You compile this code, and here's an example of a Verilog block taken from an open source hardware. This is not our hardware for obvious reasons. But the point I want to make here is that once you ship that code, the compiled code, to the fab will make the silicon. It will etch physical object, metal layers on the wafer, will print the silicon, will ship the silicon, and this is an irreversible process. It's a one-way door. Once the silicon is out, it's out. If there is a vulnerability like in this one, there's a real vulnerability found during a CTF at Hackadack 21. It was a way where this silicon was using the reset line incorrectly. So the whole posture, the whole security posture of the block and the surrounding components was compromised because of that. Well, yes, you can patch your Verilog, but that doesn't magically rewire the metal into the silicon. This will become a series of switches, physical objects, a series of transistors in the silicon. And that's why if you want to start building a solid AI compute foundation, you've got to start here. This is where you want to intercept the design of the silicon that will accelerate your AI functions and have a dedicated team that reviews the silicon with the chip architect and make sure that any known issues, any issue that is found is patched before tape out. That's what my team does. And we do the same with boards, of course. The point is that redoing a board is a little bit less expensive than redoing a silicon, but same, you want to make sure that you intercept the board design and you remove any issues before you ship it for manufacturing. And I can show you with a very silly example what the consequences can be. I don't have a real sample from our products here for obvious reasons, but I can show you one of my silly hobby projects. I wanted to make a keychain with a microcontroller and some LEDs. So I did what a professional board designer would do. I'm not a board designer. I created a schematic. I laid out the components on the board. I sent the board to the factory. The factory sent me back samples. And all the samples you see there in that box is because they're not working. The firmware was not running as I expected. It was glitching. So I started debugging. And well, I found out that I had forgot to put a trace in the right way. So what I had to do is repay the whole amount, send the code back to the factory. The factory sent me back in another 10 days the new boards, and the new boards were functioning. And here is how I patched it to confirm that it was a bug. It's a hardware patch. It's a silly example, but scale these for components that have thousands of components and have thousands of parts, and that they need to be manufactured at the speed that the current AI market is requesting. And this was also just a silly functional problem. Imagine if the board designer forgets or misconnects how the boot pins are connected to the management SoC. You might not be able to control the accelerator in the way you want. You might not be able to secure boot the SoC. You might be having an SoC that is constantly in debug mode, which means that you can access every component with the highest privileges. And we know that controlling the boot mode, controlling the strap pins, is what allows you to create a strong root of trust anchor on the system. These are the type of problems that my team focuses on. And they might look simple on the surface. I've oversimplified them a little bit on purpose. But the amount of artifacts that need to be analyzed is immense. And just one mistake can flip, as you said before, you see before, can flip the security posture of the entire component. All right, so now we have a reviewed and redesigned and manufactured component. We send it to the factory sends us back enclosures and servers, and finally we have the racks in our data centers. How do we give access to customers at this point? We want to partition these resources, but as I said before, we don't want to use any software-based isolation. We don't want to use OS-based primitives to ensure isolation, because bypassing a software isolation is much easier than bypassing a hardware-enforced isolation. But there are physical cables between these things. How do we do that? First answer is to use virtualization, right? Virtualization is something that modern CPUs all support. We have virtualization extensions virtually on every CPU. And it's something that has been around for a long, long time. The idea of virtualization is that you can run most of the instructions natively directly on the CPU without intervention of any hypervisor, or I should say virtual machine monitor, more accurately. So for example, if you have a program that needs to calculate the sum of two numbers, you can just send them to the physical CPU, and the physical CPU will happily execute them with no side effect. On the other hand, there are some instructions that are considered privileged, in the sense that they may change the isolation between guests. And you want a VMM to intercept, to trap and emulate, or to trap and do something else before sending them to the CPU. Here we have, maybe the guest is an operating system that needs to change the page tables, right? It's trying to modify the CR3 register to point to some other page tables. And we want the VMM to make sure that it saves this context somewhere in its own memory and restore that context after context switch when it needs to. Another example are input-output instructions. We cannot just send, let's say we have a guest that needs to communicate with a serial port. We cannot just send this instruction directly on the CPU, because we don't know what another guest might be doing at the same time with the same port. So we need an intervention of a VMM, and the VMM will trap this instruction, and maybe it will send it to a virtual device that implements the serial protocol, or maybe if the physical server has enough ports, it can send it to a physical port. Maybe we have 4 guests, 4 ports, every guest gets their port. But the VMM has to make sure that these are multiplexed correctly. So you might say, okay, it's done, right? Anything else that the hypervisor has to do? Of course, we need to have a useful hypervisor. We need to have storage that the machines need to have a slice. We need to have networking. We need to manage the VMs. Using Xen terminology, traditionally these functions are part of the hypervisor, and they are running in a special partition called DOM0, domain 0, which is a high privilege machine that is running and is taking care of all these functions. There are 2 issues with this design. First of all, it's high privilege. We don't want a domain that is running with high privileges, because if it gets compromised, then it will happily give away these privileges to whomever has compromised it. So we don't want this. We don't like it. The second problem is that there's a huge code base there. And you know, if you have a lot of code, you have a lot of gadget, right? So if it's exploited, then you can play more freely, let's say. So we started questioning this design, and we said, wait a minute, do we really need a shell? Do we really need a special domain running with high privileges on the main host CPU? Do we need the device models, the virtual device models, running on the same core or on the same host CPU where the customer workload is running? So in 2017, we said, let's eliminate this. Let's remove this. So we started by creating a minimized hypervisor, which is slightly more than a VMM. It just traps and emulates those special instructions and a few more. But it's basically just a VMM. And secondly, we offloaded all the device models somewhere else, outside of the host CPU. We created a PCI link, and we created these so-called Nitro cards. These are physical cards connected through PCI link that live outside of the host. These are not part of the main loop running on the host CPU. Each Nitro card has a management SoC, management microcontroller, similar to what you have seen before, and it has an ASIC to accelerate that specific function. For example, we need to accelerate networking, so we have an ASIC for networking. We need to accelerate storage, we have an ASIC for storage. The card that I showed you before, the Trainium 2 card, is basically one other example of this design. It has a management SoC, an ASIC that accelerates whatever operation you need to accelerate. And then we have a special Nitro card, which we call the Nitro controller. The Nitro controller card has a firmware that creates an interface between the EC2 control plane that receives requests from the outside. And it will be connected also to the host through PCI link. So when you create an instance using the web interface or using the command line interface, what really happens is that after your request is authenticated and is logged and anything, the EC2 control plane is contacted, and that will talk to the Nitro controller card, which will say, hey, hypervisor, I need 1 to 1,000 VMs, and I need to give them this much storage, this much network, and so on and so on. So you see, the control is passive. We don't have a shell here. We don't need to SSH into the hypervisor to create a domain and to give a virtual machine to a customer. There is a lot of complexity. I get it. There is a lot of firmware running here. And you may be wondering, how do you bootstrap all of these in a way that is still acceptable and secure? So to help me explain, let me give you a slightly simplified version of the previous diagram. We have the Nitro card below. We have the hypervisor above, CPU in the middle, a few components on the side, memory and low-speed devices. So the root of trust is the Nitro controller. The Nitro controller has a boot ROM that is statically burned onto the chip at the factory. That means that it's immutable. That cannot change. That's our trust anchor. And the nice thing about this is that we used model checking to have the mathematical proof of memory safety of the implementation of that boot ROM. So that boot ROM is immutable and has been proved to be memory safe. Then the boot ROM will start measuring the firmware running on the flash storage. If that firmware matches a signature, it uses a TPM on the side to do this measurement. If the hashes are matching, if the signature is matching, then it will start running. And the TPM has, of course, a tamper-resistant storage to hold these keys, and not only the key of the second stage firmware, but also the keys of the rest of the firmware on the system. So wait a minute. There's other stuff running on the system. How do you make sure that when you give power to the system, nothing else is running? Because silicon is programmed to do what silicon does. If you have a CPU and you give it power, the CPU will just jump to the reset vector and start running code. So we created a third component called the Nitro security chip that holds the whole system in reset. We just don't let anything else happen. The Nitro security chip will hold the system in reset. It will assert a reset signal. All the components are not running. And the Nitro controller will first measure the Nitro security chip, because we have to make sure that we are talking to a legitimate Nitro security chip. And if that measurement is matching, if the golden hashes are matching, then the other firmware images are measured. And finally, we can release, we can deassert. There's public documentation about this, by the way. We can deassert the reset signal and let the entire system run. There is a second nice property, a nice functionality implemented by the Nitro security chip. It acts as a firewall on the wire for low-speed components, such as I2C devices, such as the BIOS flash. We don't want, of course, the instances to be able to change the BIOS because that's the BIOS of the host. So we protect that with a firewall on the wire. That's the NSC. And other components as well. Of course, we want to protect components such as the voltage regulator, the fan controller. If an instance would be able to fiddle with those, anything can happen. And if you're careful, you say, hey, you obtained a system that has nice isolation property without a hypervisor. Yes, that's true. That's how our metal instances work. There's no hypervisor because we don't need that. So when you run AI workload on Nitro systems, you get these nice properties. You get a full secure booted and measured system of the entire platform firmware. The early boot code has been mathematically proved to be correct. And if you like model checking, you can read this paper. We can live update. I told you before that we could live update because we have this decoupled design. The firmware is not running as part of the main host CPU. It's running on other CPUs. It's like running on another computer. So we can live update firmware images as we need. There's no operator access because we don't need to have a shell, as I explained to you before. We have a passive design that simply creates and destroys virtual machine when needed based on an API call. So we cannot access the hypervisor. And we have this nice wire level protection of assets thanks to the Nitro security chip. Great. It's been quite a journey. So I think we can launch a new service. What do you think? I wonder if I missed something. That's what my colleague calls the elephant in the ROM. Yes, I forgot to talk about transient execution because modern CPUs have, oh, you wanted to take a picture of the elephant? I'll give you the slides later. Modern CPUs know better how to run code than you. As a programmer, you think that the CPU will respect you and just run the instructions one after another. But no, that's not the best order to run instructions. Some instructions can be run even before they're needed. They run out of order. Depending on predictive algorithms that decide on branches, that decide on pipelines, the goal is to run as many instructions as fast as possible. So you think that your code runs like this, but your code actually runs like this. So it goes from left to right. This is nice, we get nice throughput, right? But sometimes predictions are not correct. Right? So you need to roll back, the CPU will roll those back for you. That's nice. But what happens is that you may leave behind something because these CPUs have very complex cache architectures and they have a microarchitectural state that you don't get to see, but it's there. So when you unroll, when you roll back a code that has been transiently executed, some artifacts are left back in the microarchitectural case, in the microarchitectural state. And modern CPUs have quite complex cache architectures. I've tried to depict it here. I stopped at some point because it's not even accurate, not even close to accurate. There are, in addition to the hierarchy, there are cache coherency algorithms that run continuously to make sure that the core that needs the data most fresh has it there locally in their cache. So they don't need to go back and forth from memory, which is very expensive operation. So data that is frequently needed is kept fresh in cache. That's also nice, but that means that we can force data in cache. We can write a program that influences the prediction, that tells, hey, I'm going to need this data, I'm going to need this data, I'm going to need this data. So for example, you can keep accessing an array at a given index to influence the prediction. We can essentially tell the predictor, hey, we're going to take this branch at some point because I'm going to need this data. And Let's say that we have another process that has put a secret somewhere in memory, right? And has put a guard to that secret with an if bound checking, right? You would think that the program will run the correct branch. But actually, the CPU has already run both of them maybe, or the other branch, depending on which one is most probable. So what you obtain is that the secret will end up in cache. And once the secret is in cache, well, you can time it. If you have a little gadget that accesses that data in a way that you can measure how long it takes, you can make guesses. And you can guess, oh, this was short, this was fast, so it's correct. It's in cache. And if it's slow, then it's not in cache. So your guess is incorrect. So you have an oracle that lets you exfiltrate the data from the cache. And this clearly becomes an issue in virtualized environments because resource sharing at the microarchitectural level can happen by design, depending on how the hypervisor is implemented. There's another class of so-called transit execution attacks. The one before was called Spectre type of attacks. This one is the L1TF type of attack. Let's say that we have a guest that has put something in memory, a secret. Or maybe let's have the hypervisor that has put some addresses in memory because they need to keep addresses all the time. So there is something interesting in memory. And when that secret or when that information is accessed, what happens is that they will use some level of paging, and it will use, of course, some levels of page tables. I'm not even showing the complexity here. I'm showing you just one layer. But the point is that there is an expensive operation, an expensive address translation and fetching from memory that the CPU has to do. And well, because it's expensive, that secret will end up in cache. And we have seen before, once it's in cache, we can leak it. But let's see how it happens. Let's say that we have a malicious guest that is creating a weird page table. It has a present bit 0, which normally means, hey, CPU, there's nothing there yet. Just don't care. You would think that the CPU will page fault and just stop there. But as we have seen before, these executions can run out of order. So after the page fault, CPUs up to Intel Coffee Lake, I think, they will just run the instructions transiently, the instructions that come after this. And the effect is that that secret is cached. And once it's there, well, you know the drill. You can time it and you can exfiltrate it. The Nitro hypervisor is immune by design to both type of attacks. First of all, because customer instances can never share system resources. We do not let customer instances share L1 or L2 caches. And they're always running on the same core for the whole lifetime of the instance. And if we ever need to context switch, then we flush the caches. But we're not entirely happy with just this. Let's assume that we have some new transit execution attack that hasn't been discovered yet, that has a way to trick the hypervisor to access some secret in memory, secret that belongs to another guest. Once that secret is in memory, once that secret is in cache, then we can time it. And it's realistic to expect that this will happen, because we have seen L1TF can happen and can affect virtualized systems. And defending from this is extremely expensive, because you will need to continuously flush L1. It's becoming very expensive. So what we do is we deprivilege the hypervisor. The hypervisor doesn't need to have all the memory of the guest mapped in memory at all time. Only the guests need to access their data. The hypervisor doesn't need to have a top-bottom permission model where it has access to all the memory view of all the guests. We can just keep the guest that is currently running with its own memory view. So if there is a new transit execution attack that potentially can leak a secret, it'll find garbage in there because that memory doesn't exist. The hypervisor doesn't have access to that. And that's exactly what happened when we started to collaborate with a group of researchers from FUSEC in Amsterdam. They approached us saying that they wanted to try a new transit execution attack. It's quite a powerful combination because they use a half-specter gadget, which is still easy to find in hypervisor code because it's innocuous on its own. You can just load secrets in the cache, but you cannot exfiltrate it with the other half because you don't have the other half. And then they combine it with L1TF. And they managed to create a full chain, a full exploit chain that can leak secrets in this way. But because our hypervisor did not have access to that data, they were not able to leak anything sensible. So what they would find there is just irrelevant data, not guessed data. And the best thing is that we didn't need to patch for this. When we responded to this vulnerability, we didn't apply any specific patch because we were already immune by design, by deprivileging the hypervisor. So the title of this talk is Secure AI starts with secure, solid compute foundation. So how do we create solid compute foundations? Well, first of all, we need trustworthy hardware. And I need to be careful with words here because my PhD advisor is somewhere in the room. I said trustworthy. I didn't say trusted. It's a very different thing. So what we do is we design, we intercept our hardware designs, and we build them. Limited, of course, to the hardware that is core for our business. AI silicon, CPU silicon, and boards. We still verify it, though, through a dedicated hardware security team and a pen testing team. We also work on third-party hardware, of course, because we use third-party hardware. And then we need to trust, or we need a trusted firmware. So how do we do that? Well, we hold the entire system in reset until we completed all the measurements. And last, we need a hypervisor that is completely deprivileged as much as possible. We want a hypervisor that is not able to access guest data when it's not needed. So our memory view of the hypervisor is limited as much as possible. What else? Well, of course there are, and there will always be, new vulnerabilities to discover, new patches to make. Finding vulnerabilities here, though, is quite tricky. It's a pretty deep space. Even triaging vulnerabilities is very, very tricky. I've seen this morning the talk by Katie. There's no low-hanging fruits here. That's probably the fun part. So here's my ask to you. Security engineers, bug hunters, security researchers, pick hardware targets. Dig as deep as you can. Do not stop at the low-hanging fruits. And to those that are working at the higher levels of the technology stack, who are working at the application layer, if hardware looks intimidating to you, it's never too late to switch focus from software to hardware. Because secure AI starts with secure hardware. And secure hardware needs great hardware hackers, now and in the future.